Hey everybody, another day, another opportunity. I want to talk a little bit about one of my favorite ideas, which is something called algebraic geometry. It's where you take a question that is in geometry, you translate it into the language of algebra to be able to solve it, and then translate it back. And so we're just going to look at that a little bit today, and it's actually going to help you with finishing the essential assignment and also this thing that I would like to do for the final. You're going to have two choices for the final, and we'll talk about that later. But for this idea was started with this mathematician named Descartes, as far as I know, I'm pretty sure. And he created this whole thing called analytic geometry, where you look at points as x and y values, which you guys have been doing for a long time. We always have taught it that way, but it didn't used to be that way. Euclid said a point is that which has no part, very philosophical, and a line is breadthless length. So a point is that which has no part, that's nothing, is what he was. A point is a thing that's no thing. But Descartes said a point is a location in space. And you could write down what that location is if you just draw an x and y axis and you label those axes and you put where the point is. Well, then you could start talking about objects in terms of equations, and all kinds of things could happen. So that's when you take geometry but turn it into algebra. So I want to do that with this question up here. So I like this question. It's how many points are on the circle with a radius 5, centered at the origin, whose coordinates are integers? So to understand the question, we have to understand what it all means. So first of all, what's a circle? A circle is just the set of all points that are equidistant from a center point. So that's the origin, that's the point 0, 0. And then radius is 5, so every circle has a radius. That's that distance that everything is from the center, right? So if I were to draw this, we already know that I am known as the teacher who draws perfect circles. I'm not just drawing any circle, I'm drawing a circle with a certain location with a radius that's 5. So 5 up, 5 down. The center is right here at 0, 0. I'm going to mark these points 5 away. And then I've got my circle. And then I'm going to look for what are points on the circle that are integers. So, some of them you can tell right away, the ones that are exactly 5 away and on the axis. So that point is 0, 5. That point is 5, 0, 0, negative 5, negative 5, 0. Those are all integers. Integers are whole numbers, but they also include negatives. So whole numbers usually think of numbers that are like the counting numbers. Sometimes they call them the natural numbers. And those are just positive ones. But integers includes negative and positive, and we just found 4 of them. The question is that all of them? What about all these ones in between? Are any of those integers? And let's figure out how we can answer this question. Well, one way to do it is to ask a simple question. It looks like, that's 0, 5. What about the point 1, 5? It's pretty close, right? Looks like it's probably not on the circle because this goes down. But how can we prove it's not on the circle? Well, the circle decreases. This is 1. If I go up to 1, 5, that's going to be up here. It should be just above the circle. So maybe you can kind of tell that it's definitely not, but how would we prove it? Well, we can do this. Let me pick a random point on the circle. We would call it x, y, okay? And that point, I can do this to it. I can draw a line straight down. That is, that distance here is the absolute value of y. And then I can draw this here, and this thing here is the absolute value of x. In this case, x is positive and y is negative. It looks like I'm at 3, but we're going to assume it's close to 3. We don't know exactly. It just doesn't matter, x and y. Well, and this we'll call r for the radius. Radius is 5, right? Well, if you look at this here, that is a right triangle. Anytime you get a point on here, could be here too. Draw that, you could make a right triangle underneath it. And this is always going to be 5 for the radius. This will be y, that'll be x. And if we want to, actually I don't even need to write these absolute value things, I don't know why I did that. That's always x, that's always y, because in the end, if this is a right triangle, I can do the Pythagorean theorem, right? So for this and this, I could do x squared plus y squared equals r squared, or let me make this 5 squared. X squared plus y squared equals 5 squared because of the Pythagorean theorem. Anywhere on the circle that'll happen. X squared plus y squared equals 5 squared. So that actually gives me an equation. That equation is the equation of a circle. Because anywhere on the circle that'll work. X squared plus y squared equals 5 squared, because you're always going to get that same radius. That radius is always going to be the hypotenuse of your right triangle. Another way to write this? Well, if that's true, then I should be able to just put that equation in and translate the equation in, I could graph the equation. So I'm going to go to Desmos. Do that. Switch to Desmos here. I'm going to type that equation in. Let's see. X squared plus y squared equals 5 squared, or 25. And there's my circle. If you want to look at the circle and you look at the point right here that we were talking about earlier, if I try to get it where it's exactly at 1, it's 1 comma 4.899, not an integer. What if I keep traveling around the circle till I get to something that looks like an integer? I wonder if that'll work. Is that cheating if I use Desmos like this? Oh, look there. 3, 4. I can't get it to stay, but 3 comma 4 is a whole number. It looks like none of these other ones are. Keep going. That one also looks like it is. 4, 3. 3, 4, and 4, 3. Well, why did those work? That's going to work all the way around the circle because it's symmetric, right? 4, negative 3. Then I could do 3, I can't get it exactly. There. Oh, I just had it. 3, negative 4. It's going to work all the way around the circle. If we go back to our chalkboard and try to figure out why that always works, just use the equation or the Pythagorean theorem. Remember back to that time we studied Pythagorean triples. We looked at that at one point. And you guys came up with a whole bunch of different ones. And one of them was a 3, 4, 5 triangle. It's because you know that 3 squared plus 4 squared is always equal to 5 squared. Every time. So if I do negative 3 squared, I still get positive 9. negative 4 squared is still positive 16, and 5 squared is still 25. That's always true. So it could be negative 3, negative 4, negative 3, positive 4. I can switch them. So the point could be 3, negative 4, or it could be 3, positive 4, or it could be negative 3, negative 4, negative 3, positive 4. It's always, when you square them both and add them together, you're always going to get 25. If you square any other two numbers and add them together, turns out you can't get 25. And that's, again, we can prove that in other ways, but you can see it really clearly on Desmos when you look at the circle and go all the way around, that every time you get to an x integer, so what are the other integers? There's 1. Well, if I solve that equation and replace x with 1, I get y squared, so if I do 1 squared plus y squared equals 25, I get y squared equals 24, and y is the square root of 24. 24 is not a perfect square, so it's not going to be an integer. Same if you do 2. 2 squared plus y squared is 25, and you get 4 plus y squared equals 25. Y squared equals 21. Take the square root, then you get not a perfect square, right? So it doesn't work for 1, doesn't work for 2, but it works for 3, works for 4, and then it won't work for 5 either. You can check that as well. Oh no, it does work for 5, I'm sorry, because that lands right down here. So in the end, what are all of the perfect, the integer values? We've got 3, 4, 3. So we've got 1, 2, 3, 4 here, 5, 6, 7, 8, 9, 10, 11, 12, and that's it. There are 12 points on that circle that are integers. There are infinitely many points that are not. So that's the answer to that question. So if you ever want to check if a point is on a circle and you have the equation of a circle, all you have to do is replace the x and y values of the point and see if when you square them and add them together, they give you the same thing as the radius squared. That is actually one of the problems on your essential assignment. I think it's problem number 7. It's just different numbers than this. I hope, unless I remember it wrong. Anyway, we'll talk more.